Lesson 2.2, Inductive and Deductive Reasoning. If You Give a Mouse a Cookie, that's a book that a lot of us have read, or someone read it to us. And it's similar to the kind of reasoning we're going to be looking at later on, a chain of reasoning. Our essential question, how can you compare and contrast inductive and deductive reasoning? So we're going to be looking at two types of reasoning. Take a minute to set up your notebook with the title, the essential question, and the different vocabulary words. Notice that I left some room for an example. So once you understand law of detachment and law of syllogism, then you're going to want to write an example in there. Let's first talk about a conjecture. Write a conjecture about the pattern, then use your conjecture to draw the 10th object. Okay, I'm noticing a pattern that this circle here is on the right hand side, then on the left hand side, then on the top, then on the right hand, left hand, top, left hand. So if I continue in the same pattern that I'm seeing, number 8 will then be a circle on the right hand side, number 9 will be a circle on the top, and number 10 will be a circle on the right hand. I'm going to just do one more. I'm going to look at the pattern. It looks like a curve on this first quadrant. Then this quadrant is a straight line, a curve, a straight line, a curve, a straight line, a curve. And so this one is going to have the straight line. This one will have the curve. And then this 10th one is going to have the straight line. And I'm not going to do part C. But this is an example of looking at patterns. What do we call this? Well, we call this inductive reasoning. A conjecture is an unproven statement that is based on observation. So all my conclusions were conjectures, and this is called an inductive reasoning. Let's do it one more time. Describe how to sketch the fourth figure in the pattern. So I'm talking out loud. It looks like it's in half, and we shade the upper half. Then I'm doing it in fourths, and I'm shading it to the left. Then looks like I'm shading it to 6. So this is 2, 4, 6. So it looks like it's being cut in even numbers. So I'm going to assume that it's going to be 4, and I'm always going to shade, looks like this portion I always shade. And again, that's a conjecture on my part. That's a guess that I'm thinking through the pattern. Now sometimes when we're looking at conjectures, we might not come across the right conjecture. We might not guess right. And a counterexample is an example that shows us that we didn't make a very good guess. Okay, so here's a conjecture. Somebody made a guess. The sum of two numbers is always more than the greater number. Okay, so let's put some numbers down, like 3 plus 2 is equal to 5. And you can see that 5 is greater than the greater number right here. Well, that's a true statement. I'm trying to prove that this is false. And so let me think about using numbers that are maybe not positive, like maybe instead of -3 plus -2 equals -5. Now we know that this number is less than the greater of these two. This is the greater of the two numbers. And I am showing that this sentence does not make sense. This is a counterexample. It's showing an example that proves the statement is false. So here is a number that is not greater than more than the greater number. Now this proves that is true. So proving something that is true is not a counterexample. Counterexample is when you show that it is false. Okay, so let's go ahead and practice finding a counterexample. All rectangles are squares. And so I'm going to draw a picture of a rectangle that is not a square. Okay, so here is a rectangle. This is a counterexample. I'm showing you can draw a rectangle and it makes the sentence incorrect. All right, I want to have a counterexample here. Now, x squared is equal to 4, then x is equal to 2. And my counterexample is x could be negative 2. It doesn't have to be 2. It could be negative 2. So both of those are counterexamples. Okay, let's go into deductive reasoning. That's the second type of reasoning, and that's the kind of reasoning we use a lot of in geometry. We're going to use facts, definitions, accepted properties, and laws of logic to form a logical argument. And this is different from inductive when we're just looking at a pattern. Okay, the first law that we're going to use is law of detachment. If the hypothesis of a true statement is true, then the conclusion is true. And then we're going to use the law of syllogism. The law of syllogism is like that if you give a mouse a cookie, then he wants a glass of milk. If he has a glass of milk, then he wants a straw. If he wants a straw, then he asks for a napkin. There's also a very famous commercial, I think DirecTV, that says, if you have cable, then something happens. Then if this happens, then something else happens, and so on. So DirecTV really got onto the bandwagon with this kind of law of syllogism. So it starts off, if the hypothesis is P, then here's your conclusion. And then you start with your conclusion. You start with the Q words, and then you make another conclusion. And you can keep doing this like they do in the commercial or in the book. But the fact of the matter is, when you start with P, then you end up with the R conclusion. And this is how the law of syllogism works. If that doesn't seem too clear, I have some examples for you. First, let's take a look at the law of detachment. Notice that I have an if-then statement. So I'm going to say P implies Q. So this is an if-then statement. And Patches is a dog. So he's part of the hypothesis. So that's P. And if you can get that item into the hypothesis, then your conclusion is Q. Okay. Another way that helps students is if I draw a Venn diagram. So this big set is called mammals. And in this big set are called dogs. So dogs are a little portion of mammals. And Patches belongs right here. He belongs in the dog set. And if he belongs in the dog set, he belongs in the mammal set. So that's why I'm making that kind of reasoning. Okay, let's do it again. If an animal is a dog, then it is a mammal. And remember that this, the conclusion is the big group, mammals. And the hypothesis is the little group, which are dogs. Now, the second sentence says Patches is a mammal. Now, Patches is being a mammal. He doesn't have to be in the dog. He could be right here. He could be an elephant or something else like that. So we have this. We have Patches. We have Q. And this is not the kind of reasoning we use the law of detachment. We want to ensure that this item is part of the little group. So this reasoning does not work, and we say no conclusion. We're not using the law of detachment correctly. The law of detachment has to go like this. P implies Q. You've got to address the P, the hypothesis, then you can make the conclusion about Q. Let's take a look at the law of syllogism, that chain of reasoning. Okay, and here is something like P implies Q, where P is the square words and Q is the rectangle words. And this right here talks about rectangle, so that's a Q, and it implies another word, parallelogram, so we'll say R. Now, when you see that chain of reasoning, that connection right here, where the end and the beginning are the same, then we can say this beginning part, A, B, C, D, is a square, and we can say with this chain of reasoning, we can conclude it is a parallelogram. So this is how the law of syllogism works. Okay, let's try this one. P implies Q. So the P is you are a Mustang, and the Q is Dobson. Now notice there is no connection. We are not, this and this are not connecting. We're starting with P again and going to something else, which is R. There is no connection, so we say there is no conclusion. When you're learning, sometimes it's important to see something that doesn't work, so it makes you understand that better. Okay, now we have two examples. We want to decide whether it's inductive or deductive reasoning. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball in the air, it will return to the ground. This looks like she's looking at a pattern. And when she's looking at a pattern, this is called inductive reasoning. Inductive reasoning is looking at patterns. Okay, the next one says all reptiles, P, are cold-blooded, which is Q. So P implies Q. And it looks like lizards are reptiles. So we're putting it in the hypothesis. That's P. So then if lizards are part of the group, here's the big circle, cold-blooded. And inside here is reptiles. And we're going to have lizards in here. So once lizards are part of this, then we know they're cold-blooded. So this is the Q part. So this is an example of deductive reasoning where we're using one of the laws. All right, let's take a look at using the law of detachment. Okay, so here's the P and here's the Q. And it says the measure of angle R is 155. So 155 is part of our P. So it looks like it's following the pattern correctly. So what statement can we make? We can say angle R is obtuse. Okay, now let's use the law of syllogism. This is that chain of reasoning here. If you get an A on your math test, then you go to the movies. So this is P implies Q. And you can see here, this is Q. So there's a good connection, like a chain. And then this is another statement, R. So we can say, if you get an A, then you watch your favorite actor. All right, at this point, I want you to think about inductive reasoning and deductive reasoning and compare what they are and contrast, and that'll help you write your summary. This is the end of the screencast.